Hello friends, today we are going to see moment distribution method. This is problem 1 of the series for moment distribution method. I have also solved the same problem using Kani's method, and you can see this in my Kani's method tutorials, and you can match the answers later on. Alright, so step 1 for moment distribution method is, as you can see this problem, both the ends are fixed, and our my assumption is that you know what are fixed end moments already, okay, and how they are calculated. The formula is, I think, well versed for you. All right, and our primary assumption before solving any type of indeterminate beams is that except the end joints, that is in this case A and D, all the other joints, all the intermediate joints, that is B and C, are considered to be fixed. Okay, that is the reason we find fixed end moments, because any load that is applied between two joints will produce moments which are equal to fixed end moments, because this is already fixed, this I'm considering as fixed. That's my assumption, right? Primary assumption. So the moment that would be produced would be fixed end moments. Okay, so let us start with our step 1, that is finding fixed end moments. MFAB is fixed end moment at A, okay, and it is given as minus of WAB square by L square, where W is equal to 80, A is 1, B is 2, and L is 3. Okay, so we get minus 35.556. Now the reason that I've put a minus sign here is that, as per my convention, anti-clockwise is negative. Okay, and if you see this 80 kilonewton load, this will try to sag my beam. Okay, sag this portion AB like this. I'll bend it in this manner, and there will be an anti-clockwise resisting moment that is formed here, and anti-clockwise, as per my sign convention, is negative. That is the reason I've taken negative sign here. Okay, we'll see now MFBA, that is fixed end moment at B to A, and it is given as WA square B by L square positive, where W is 80, A is again 1, B is 2, and L is the length of the segment AB, and it comes out to be 17.778 kilonewton meter. Okay, now MFBC, fixed end moment at B to C, it is given by minus WL square by 12, since it's a UDL spanning throughout the segmental length. Okay, and where W is 50, L is 4 meters, and MFBC, we get it as minus 66.667, the negative sign indicating it as an anti-clockwise moment. MFCB is equal to plus WL square by 12, and it is equal to 66.667 kilonewton meter. MFCD, this fixed end moment from C to D, it is given as minus WAB square by L square, where W is 40, A is 2, B is 2, L is 4. You can also use the formula of minus WL by 8, since the load is acting centrally. Okay, but I prefer choosing this formula, as it is a general formula, and you don't have to remember two formulas for the same thing. Okay, and you get the answer as minus 20 kilonewton meter, and MFDC is equal to WA square B by L square, it is equal to 20 kilonewton meter. Alright, through with the fixed end moments. This was a step 1 which is done. Okay, now step 2. Step 2 is calculating distribution factor. Now distribution factor is very important for moment distribution method. Okay, and it has this, we can calculate distribution factor by drawing a table. I'll explain you this table. It consists of the intermediate joints, all the intermediate joints. Okay, in our case there are only two intermediate joints, that is B and C, and why are they called intermediate joints? Because they connect more than one members. Okay, yeah, because they connect more than one members. BA, BC for B, and C is CB and CD. Alright, so first column is joint, which is B and C. Second is the members that are connected by the respective joints, that is BABC for B and CBCD for C. And third column is relative stiffness. Now For those who don't know what relative stiffness is, I'll actually explain you the formula of how you get relative stiffness. When I consider my member BA, or when I consider my intermediate joint B, if the far off end, that is for BA, the far off end would be A. This is called as a far off end for member BA. Okay, for member BC, the far off end would be C. So if my far off end is fixed, my relative stiffness formula is EI by L. Okay, and if my far off end is hinged or pin jointed, that is, if suppose this was a roller or this was a hinge and it was pin jointed, then my relative stiffness formula would be 3 by 4 EI by L. Okay, so here we have fixed, so it is EI by L. Again, BC, far off end is C, and C, as per our primary assumption, it's an intermediate joint, so it is also fixed, so it is EI by L again. Okay, similarly for CB, B is the far off end and B is fixed, so it is EI by L, and for CD, D is the far off end and D is fixed as well, so it's EI by L. Okay, now care is to be taken that EI for every member is changing, so relative stiffness will also not be same for, though their formula is same, but it won't be same for all the members. So for BA it is E into 1.5I by L. L is a member length. For BC it is E into 2I by L, where L is again the member length of BC. For CB it is E into 2I by L, that is 4, and for CD it is E into I by L. What is total relative stiffness? It is the summation of relative stiffness of members connecting the joint. So total relative stiffness for joint B would be relative stiffness of BA plus relative stiffness of BC. So total relative stiffness, if I add them, I get EI. Okay, and for joint C, if I add these two, I get 3 by 4 EI. Fine. Now what is distribution factor? The thing that we have to find distribution factor is basically relative stiffness of the member divided by total relative stiffness. Okay, so if I divide this by this, I get 0.5. Okay, and if I divide this by this, I get 0.5 again. So for member BA it is 0.5, for member BC it is 0.5, for member CB if I divide 2 by 4 EI by 3 by 4 EI, I get 2 by 3, and for CD if I divide EI by 4 divided by 3 by 4 EI, I get 1 by 3. So I've found all the distribution factors and my step 2 is complete. Okay, let's move on to step 3. That is our main moment distribution. Okay, now I have just drawn the beam A, B, C, D, and these are my intermediate supports, and I've drawn the boxes as you can see. Now we have to fill values in these boxes. I'll tell you how to fill values. First is we'll write all the distribution factors. Okay, 0.5 was for BA, 0.5 was for BC, 2 by 3 for CB, and 1 by 3 for CD. A and D won't have any distribution factor as we saw earlier as well in step 2. Okay, then just below them we have to write all the fixed end moments: MFAB, MFBA, MFBC, MFCB, MFCD, and MFDC. Okay, now there's a concept that I'll be teaching you right now. Okay, consider this joint B and consider the fixed end moments here: 17.778 and minus 66.667. okay, 17.778, since it's positive, it's a clockwise movement, and minus 66.667, since it's negative, it's a anti-clockwise movement. Okay, so both these moments are acting at a single joint, so they will form a resultant, right? I can just add them up, and by adding them up I'll get a resultant of negative, that is anti-clockwise moment, of 48.889. It's just simple addition of these two. Okay, and this anti-clockwise moment will try to rotate my beam in such a way. Do you see this shape? So it has rotated my beam at the joint B. Okay, in reality there is no structure in which a joint is rotated, or civil engineers do not permit structures where joint is rotated, because rotation of joint basically means that the structure has failed, and we do not permit any failure of the structures. Okay, so this cannot be permitted, minus 48.889. Thus, to counteract this, we have to additionally provide a 48 plus 48.889 clockwise movement. So you see this anti-clockwise movement gets negated by when we add plus 48.889. So this 48.889 we have added to the beam. Basically, uh, in practical reasons, we cannot add such movement. Okay, like we cannot externally add movements. It is the strength of the beam itself which will try to resist this minus 48.889, and it itself will give this positive 48.889 from its own strength. Okay, the beam can be made of concrete, it can be of steel, or it can be of wooden, or for that matter any material, and any material has its own strength, right? So it will take the moment from its own strength, and member BA and member BC will contribute to this moment. Okay, so some part of 48.889 will come from member BA, and some part of 48.889 will come from member BC. So how much part would be from BA and how much part would be from BC, we get that from our distribution factors. Okay, so yeah, see, you see, when I uh, give this 48.889 positive, my beam becomes straight again. And now how much part of 48.889 is given by BA is 48.889 into its distribution factor. So contribution by BA is 24.445 and contribution by BC is again 24.445, because their distribution factors are same. You get it? I hope this concept was very clear, and these values are what we require. The values written in red are what we require in our moment distribution iteration. Okay, we'll see this once again for joint C. Okay, you see a 66.667 is positive, that means it's clockwise, and this is negative, it means it's anti-clockwise. So the resultant, since this is greater, the resultant would be also a clockwise movement of 46.667 kilonewton meter, and it's clockwise. So it will try to rotate my beam like this. You see the deflected chain. Since my beam does not want to rotate, it itself will counteract this 46.667 by an anti-clockwise movement, which is given by minus 46.667, and see, the beam has become straight again. But how much part of this 46.667 was contributed by CB and how much by CD would be given by my distribution factors. So if I multiply this by 2 by 3, I'll get the contribution by CB, and if I multiply this by 1 by 3, I'll get the contribution by CD. You get this? Okay, so now we'll proceed ahead for our main moment distribution iterations here. So let us start with first iteration. Okay, the first step is balancing the moment. As you can see, there is an anti-clockwise moment on my beam, on my joint, I'm sorry, anti-clockwise moment of minus 48.889. Thus, to balance it, my beam will apply a moment of 48.889, and its contribution would be given by, this is the first balancing step. Okay, second step is distribution step, that is the contribution step, as you can see. So contribution by this would be 24.445 and again 24.445. all right, here on joint C, the balancing is basically minus 46.667. Why? Because there was a clockwise movement of 46 plus 46.667, and thus my beam had to produce an additional minus 46.667 to counteract it, and the contribution is given as minus 31.111 and minus 15.556. How did I get this? I multiplied this value by its distribution factors. So this is my distribution step. First is balancing step, second is distribution step, and third Okay, you might want to know how I got these values as 0. Since there was no balancing done here, so of course there won't be any distribution done as well. Same here, since there is no balancing done here, there is no distribution from this joint. Okay, and uh, I have deliberately not done balancing here because it's a fixed support, and fixed support are capable of carrying moments. Okay, that is the reason I have not done the balancing. Third step is carry over. Okay, this is very simple. I just have to carry over this value to the opposite direction, and then I have to multiply it by half. So 24.445 into half is 12.223, and 0 is obviously 0. Again we have to carry over here, this goes here and becomes 12.223, this comes here and it becomes minus 15.556. Carry over. Again this will go here and this will come here. So this is my third step, carry over step. Now we'll move to the next iteration. Okay, again same steps we have to follow. First it would be balancing. Now balancing is done for these. Okay, see, you can see here this is an unbalanced moment of minus 15.556. that is, there's an anti-clockwise moment of 15.556 produced on my support, and my beam is counteracting it by providing an clockwise moment of 15.556. The contribution would be given as 7.778. that is, I have multiplied this by its distribution factors. Okay, and here again there was a 12.223 clockwise movement that was acting on the support, and thus my beam produced an anti-clockwise movement to counteract it, and I have to multiply it by the distribution factor. I get its this contribution by CB and CD. Okay, by multiplying the distribution factors, and here again it's 0 at the ends. And our third step is carry over. Okay, so 0 comes here, 0, 7.778 becomes 3.889. Okay, I have just multiplied it by half. Again here 7.778 becomes 3.889. This becomes minus 4.074. Okay, and again here it's minus 2.037, and 0 is 0. Alright, so this was our second iteration. Now we'll go for third iteration. Again first is balancing. So this is my unbalanced moment here, I'll balance it. Okay, again here this was an unbalanced moment, I have balanced it. Second is distribution. I will multiply this by its distribution factor to get the distribution values or the contributing values. Again I'll multiply this by its respective distribution factors to get the contributing or distributing values, and here of course it's 0. Third step is carry over again. So carry over meaning this becomes 0, this becomes 1.0185, this becomes 1.0185, this is minus 1.2963, this is minus 0.6482, and this is 0. Third iteration. Fourth iteration, again I will balance this, that is, the beam will produce a clockwise moment of 1.2963 to balance the anti-clockwise moment. Here it will produce a clockwise moment, it will produce an anti-clockwise moment of minus 1.0185. The balancing step. Second, distribution step, multiplying this by its distribution factor, multiplying this by its distribution factor. Third is carry over step. So I just carry over it and multiply it by half, again here and here as well. 1 2 3 4 4 iterations are over. This is our fifth iteration. You have to keep on iterating it till you get this value as very small value. Okay, so we'll check if we get a very small value. So you can see we are getting 0.0849. okay, it's a very small value. 0.1 is not so small, but it's okay if we It's okay if we keep it as 0.18, 0.108, but you can see most of the values are uh, getting lesser than 0.08. Okay, so 5 iterations are enough, but the thing is that you cannot end it over the carryover step. Okay, you cannot end the moment distribution method at the carryover. So what I'm going to do is I'm going to again do another iteration, but this time it will only be till the distribution step. Okay, remember, always end your MDM iterations on the distribution step, never to end it on balancing step or carryover step. Okay, you should never end it on balancing or carryover step. You should always end it on distribution step. So although we were getting here very low values, but we could not end it over carryover step, thus we did another iteration and ended it over distribution step. Now this is our final step, and we just have to add all the values now. Okay, so by adding all these values, minus 35.556, 12.223, 3.889, 1.0185, 0.3241, 0.0849, we get as minus 18.0165. Okay, here again when we add all these values, all the values to the left hand side, the middle values are not to be added. Okay, now since this is a tutorial, that is the reason I was writing these middle values, but as you practice more and more, you'll be capable enough of not of avoiding these values. Okay, and because these values have nothing to do with the final moments, you don't have to add them, don't have to subtract them, don't have to do anything with them, so you just you can avoid it further. Okay, and just add these values. Okay, and again we'll add these values now: minus 66.667, 24.445, minus 15.556, plus 7.778, minus 4.074, plus 2.037, minus 1.2963, this value, this value, this value, this value, and this value. So we get it as minus 52.91. Again same thing to be done here, and you have to start your addition from these values. Okay, from your fixed end moments, and you have to add all the values right to the last step, right to the distribution step. So these are my final moments, and you can see that these moments have to match. Okay, match in magnitude, but they have to be uh, of alternate nature. That is, if this is positive, this has to be negative. If this is positive, this is negative. This is negative, this is positive, but the magnitude of both the values is same. So this ends our moment distribution method. Okay, if you have any queries, you can write down in the comment section, and we have successfully analyzed our problem. Thank you.